Okay, so in the first component, which is spring, when we add displacement to the spring, whether it is compression or tensile extension, so force will be created. So the formula is force is equal to the stiffness times the displacement. So K is the stiffness. Alright. So that's how we create force in spring. Now we go to the damper. So in damper, if there is displacement inside the damper, it doesn't mean it will have force. Okay. Remember, if there is displacement D in a damper, it doesn't mean it will have force unless there is velocity. If there is velocity, then there will be force. Okay. So the formula is for a damper is force is equal to viscosity, which is C, time the velocity. Like I said, in the formula there is no displacement. It only have velocity. So the person who want to push the damper should have velocity in its push. Okay. Alright. So we go to the next one is the mass. Now we consider about the acceleration. Alright. When we push the mass, for example, we ignore the friction on the floor. We have wheel. So if we push it with a constant velocity, can you remember? If the velocity is constant, there is no acceleration, zero acceleration, there will be no force created. Okay. So it's like when we push a trolley. When we push trolley, but when the velocity is constant, we will feel that it is very easy to push it, because actually there is no force created except the force that we consider the force we exert to overcome the friction force. Okay. Remember in this in the mass configuration, when there is no acceleration, okay, when there is no acceleration, there is no force. But when there is acceleration, and if you look at this final diagram, the person is accelerating the velocity. So that means the velocity is increasing, therefore there is force. Okay. So when we consider about a mass, there will only have force when there is acceleration. So the formula is force is equal to mass time acceleration. Okay. Okay, why do we measure vibration? Alright. So before this, the three equation is to measure the component of the vibration. So it is we measure vibration is to verify that the frequency and amplitude within a machine or within a system do not exceed the material limits. Okay, each material has its limits. When some material can sustain high vibration, but some cannot. So if the vibration frequencies or amplitude exceed the material limit, the material will fail. Okay, next is to avoid excitation of resonance in certain parts of a machine. So what is resonance? We will learn about that afterward. Okay. So basically resonance is when the frequency is equal to the natural frequency of a particular system. So the machine will vibrate very badly, which is the amplitude is high. Okay. Now the third one is to be able to dampen or isolate vibration sources. So yes, we measure vibration because we want to eliminate the vibration. Sometimes vibration is useful, but most of the time we want to control the vibration, either to remove it or to dampen it. Okay. The first one is to make conditional maintenance on machine. So when a vibration occur, there will be fatigue, there will be wear and tear. So we want to measure the severity of the vibration, and from that we can know how long a machine can the life of the machine. We can know the life of the machine according to the type of vibration and so on. And the last one is to construct or verify computer models of structure. So this is basically related to computational or simulation. So we want to compare. So currently we have many software that we can use to simulate vibration in the system. So we can use it to ease our work in measuring vibration. Right. So this is the simplest form of vibrating system. So it is in the form of sinusoidal wave. So we consider this simple system, which is a spring and a mass, and there is an indicator to draw the vibration. All right. So the displacement is in sinusoidal shape against the time. But when we consider the displacement against the frequency is constant in and the formula for the frequency is 1 over the period t. So the period is constant, but the displacement this is equal to d, similar to this d. Alright. Okay. So period is in second, and frequency is the unit is hertz, which is equal to 1 over a second. And from usually we want to calculate this component omega n. We call it natural frequency. So natural frequency is we measure. This is the equation for natural frequency, 2 pi f. Okay. So Fn is the frequency when there is free. This is free. Free vibration. Because there is no external force. When there is free vibration, and we measure the frequency, so that's the frequency for the free vibration. And when we put inside this formula, we can calculate the natural frequency. And this is another formula for natural frequency, which is we consider the K, the stiffness of the spring, and also the mass. So what will change if we, for example, in this case, we increase the mass. When we increase the mass, so m plus m1, so this is m1. So what happens is the frequency will reduce. The frequency will be reduced. Okay, and also the natural frequency will also be reduced. So if you look at in this diagram, the green vibration is the previous curves for the free vibration, but the blue one is after we add the mass. So if you look at the curve, the period is increased after the mass is increased. Therefore, the frequency is decreased. Next, what happens if we add damper? So previously there is no damper, but after right now we have damper right here. So if we add one damper, for example C1, so what will happen is the green line, the green line. So that is for C1 alone. And after that, we add another damper, the smaller one, C2. So what will happen is the line change to the blue line. The green line change to the blue line, and we can see that increasing damping reduce the amplitude. So the amplitude is decreased. Again, what is amplitude? Amplitude is the maximum displacement. So the first amplitude is this one. I mean, this is the previous amplitude, and this is the second amplitude after we add the more damper. Okay, hopefully you got that. Now we want to consider a system, and from the system we want to produce equation from the vibrating system. So the first one is undamped free vibration. So when a vibration is undamped, it can continue infinitely without stopping. If there is no damper and there is no friction, the system can vibrate eternally. Okay. But in reality, motion of all vibrating bodies is actually damped because of friction. So either it is air friction, surface friction, and so on. Okay. So this is the example of free vibration, and it is undamped. Okay, because we consider that the surface, the floor surface, has no friction. Alright. So again, we have the stiffness K. The displacement, we can consider it as D or X. We can also have mass. Okay, we have mass. Alright. So this is the equilibrium. This is the equilibrium position. That means this spring has been stretched. this mass has this mass has stretched the spring. Okay, the block has mass m, and it is attached to a spring with this stiffness k. When released from a displaced position x, so like I said, the spring has been displaced. The spring will pull the block back to the in order to compress the spring back to the initial position. Okay, so by releasing the mass, when the mass is going back to the initial position, it will exit the initial position, and there will be compression to the spring, and then the spring will push back the mass to go back to the initial position, but again it will exit, and it will extend the spring, and this process goes on forever if there is no friction. Okay, so that is what we call as vibrating motion. So the block will attain a velocity such that it will proceed to move out of equilibrium. So equilibrium, that is the equilibrium point is the initial point where there is no force applied. Okay, so the equilibrium is when x is equal to 0. That's the equilibrium point. Again, the surface is smooth, there's no friction. Okay, so the vibration can continue eternally. Okay, the time-dependent path of motion of the block may be determined by applying equation of motion to the block. Okay, we want to now we want to create the equation related to the system just now. Alright, so we have the x, the displacement, we know the stiffness of the spring. From there we can calculate the force. So the elastic restoring force, F, the equation is F equal to Kx. This is the Hooke law. And this force is always directed toward the equilibrium position, right? So we have the spring right here. So this is the equilibrium position. Okay, so the force will always directed to the equilibrium position, but when the mass is right here, so it vibrates from the left and right. So when the mass is right here, the spring is compressed, so the force is in the direction to the right, because the equilibrium position is at the right. Okay, okay, when we consider acceleration, okay, this is quite tricky, but you need to always remember that when we consider acceleration, we always assume that it is in the direction of positive displacement. Okay. There is another component we will see after this, but you need to remember that the acceleration is assumed to act in a direction of positive displacement. So positive displacement is in this direction. So this is x equal to 0. Okay, so this is x equal to any value.